Okay. Okay, we are talking about cache, right? And big picture first. Big picture. Cache is placed between CPU and main memory. Okay, it is very small, very small. 8 megabyte, for example, in Intel processor case, 8 megabyte. And how big your main memory? 8 gigabyte, right? Roughly. So roughly 1,000 times smaller cache, right? 1,000 times smaller than main memory. But it is ultra fast, super fast. Okay, a super fast memory. So when you turn on the computer, cache does not have anything. There's nothing. Okay, there's nothing inside the cache, and CPU request instruction or data, like CPU read instruction or CPU read data or write data, and cache will store the requested information. Okay, request information from memory to cache automatically for you. Okay, again, when CPU reads instruction from memory or data or access data from memory, cache will store that requested information from memory to the cache. Okay, let me draw big picture. We have cache and memory, right? DRAM, DDR. So when you turn on the computer, that is, for example, Intel CPU, Core i7. Okay. So when you turn on computer, there's nothing. There's no data, nothing. Okay, nothing inside cache. It is SRAM based design, meaning if you turn on the computer, the information is gone, right? No information is left. So nothing is left when you turn off. So you turn on the computer, right? Then CPU read instruction patch, and from actually the memory, right? And also data access. So at the beginning, cache is not able to provide instruction or data because there's nothing, right? So main memory will provide that information to CPU, right? But what happens is when memory provide that information to CPU, cache will store that information. Okay, store that information inside the cache. Then next time CPU request same information. Okay, same information. Request the same information. Then CPU do not have to access this slow memory. Okay, cache is able to provide that information to CPU directly because it is caching. It is storing that information. Okay, that is big picture. Okay, small ultra fast memory. Okay, computer system, right? The motherboard. We have a processor and main memory and I/O devices, and caches are located inside that processor. Okay, inside the processor. So we are talking about cache inside that processor. Okay. Okay, this one, Seungmin, can you please?
Core 2 Duo Intel, 32 kilobyte 8-way 64-byte line LRU WB 3-cycle latency. L2, 4.0 megabyte 16-way 64-byte line LRU WB 14 cycle latency.
Okay, some mysterious terminologies, right? 8-way, right? 8-way set associative structure, and 64 bytes per cache line, LRU, least recently used, write cache, and cycle access latency. So don't worry too much about it. Okay, sorry. Okay, some unknown, terminologies, right? So for now, don't worry too much about this. We'll get to that, right? After cache discussion, you will understand what those terminologies mean. Okay, don't worry too much about this. But big picture. Call to Duo. If you open this package, then you are able to see this block diagram. So almost half of this real estate silicon, right? This silicon. Open this package and take a picture. Then you see this. Almost half of real estate is used by cache. So this one, L2 means level 2 cache. That means there is a level 1. Yes, level 1 here. We have a level 1 I cache, instruction cache. Okay, so that means that cache is storing only instructions. Okay, no data. And this one, data, level 1 cache, but it is storing only data. Okay, level 2 cache is storing both instruction and data. Okay, so in this Core to Duo is 10 years old, more than 10 years old CPU, a processor from Intel. So Duo, so we have two CPU cores, and each core has private level 1 caches, right? Private instruction cache and data cache. And second core, same thing, right? Instruction cache and data cache. And level 2 cache is shared between these two. Okay, so level 2 cache serves both core 0 and core 1. And also unified cache, meaning it holds both instruction and data. Okay, so that is rough configuration. Okay, this one, Sam.
Core i7 Intel, 4-core on a chip, 3 levels of caches, L1, L2, L3 on the chip, L1 32 kilobyte 8-way, L2 256 kilobyte 8-way, L3 8 megabyte 16-way, 731 million transistors in 263 millimeter square with 45 nanometer technology.
Okay, thanks. Some information. First generation of Core i7. First Core i7. It is rolled out, I think, 10 years ago, 2010, 2008, 2009 or 10. Okay, so around that time frame. Core i7, it has 4 CPUs, right? 1, 2, 3, 4, and it has big. It has one more level of cache, level 3 cache. Okay, size 8 megabyte, and each CPU, each core has private level 1, level 2 caches. Okay, so level 1 cache 32 kilobyte, level 2 256 kilobyte. I think this one, and this one, these two are level 2 caches. Okay, and level 1 cache is too small. I cannot spot which one is level 1. Probably this one, these two. How many transistors? 731 million transistor. In Korean, 7억, right? 7.3억, right? that many transistors are packed in thumbnail-sized, this is thumbnail-sized space. That is rough dimension, 263 square millimeter. Okay. So, and it is using 45 nanometer semiconductor technology. Transistor size 45 nanometer. About second generation Core i7, I was involved in this project when I was work for Intel back in 2008. Look at this, second generation, four CPUs and big level 3 cache, right? And we have one more. Comparing these two, first generation, 4 CPUs, right, cache, and second generation. So you see this, right? A big graphics engine. So that used to be graphics engine used to be in Northbridge, that chip. But because of the semiconductor technology, Intel was able to merge these two. You put these two together, right? This one and that one together. Okay. So now, Intel processor has graphics engine inside, processor. So if you do not gaming, then probably you don't have to purchase, separate graphics card, NVIDIA graphics card, right? If you just do internet surfing and watch, YouTube video, right? You don't have to purchase, graphics card. That engine will do that job, more than enough job, right? The graphics engine. Second generation, it is using 32 nanometer semiconductor technology. Compare these two, 45, first generation, and then the size is getting smaller and smaller, right? 32 nanometer technology. Transistor count, close to 1 billion. In Korean, 10억, right? 10억 transistors, close to 1 billion. Third generation, okay, similar configuration. Compare these two. Compare rough picture. Compare these two rough, pictures. This one and this one. Okay, this one. So the difference is graphics engine beefed up. It is getting bigger and bigger, right? And CPUs, 4 CPUs, same levels of cache. Cache size is the same, 64K, 256. Compare these two, 32, 8, right? Same, right? And transistor count, 1.4 billion, 14 billion transistors. How many people live on Earth? 8 billion, I think. 7 to 8 billion people live on Earth, right? And look at the transistor count, 1.4. And how? Roughly, 1/5, right? 1/5. Earth's population, Earth's human population, Earth's transistors are living in this thumbnail-sized, space. If one transistor fails, then CPU processor does not work, right? So 1.4 or 1.4 billion transistors should work, right? Should work properly. It's amazing technology, right? Amazing. 1/5, Earth's population Earth's transistors, right? Same message. So let's skip this. AMD processor Barcelona introduced in 2007. Similar configuration, 4 CPUs, similar cache levels. Let's skip this. Okay, this one is important. Jisang, can you please?
Take advantage of principle of ability to present the user with as much memory as is available in the cheapest technology at the speed offered by the fastest technology.
Okay, so what do we want to achieve? What do you want to achieve by placing a cache? By placing that cache, let me pick up a little bit. So we have this slide is focusing on memory components. Okay, memory components inside the computer. Okay, what kind of memory components you have? First one you can think of is hard disk or SSD, which is called secondary storage, right? Hard disk or SSD, solid state drive. And then we have register file inside the CPU. Okay, so in between these two, we have main memory, right? DIMM module. Have you seen that picture? DIMM module. This one. That DIMM module, right? That is actually main memory inside your notebook computer or desktop computer. Main memory DIMM, dual inline module. Okay, and each one you have 1, 2, 3, 4, 5, 6, 7, 8. Each one is called DDR chip. DDR, double data rate, synchronous SDRAM. Each one is DDR, double data rate. And something is hidden here, SDRAM. It is DRAM, okay? Dynamic random access memory. S means synchronous. SYN, synchronous. CHRONOUS, synchronous, okay? Synchronous. Synchronous means what? You have clock coming in. Clock is coming in, right? So that is main memory. Okay, so that main memory, DRAM, right? DDR is located here. Okay, and not only these, three, but we have in this case, I drew only two levels of caches: level 1 cache, level 1 caches, and level 2. Okay, and you have level 3 cache. Okay, in Intel processor. So here, level 1 cache, L1 I means instruction cache. It is holding only instructions, no data, only instructions. L1D, D means data cache, no instructions, only data. Okay, data cache. And level 2 cache is unified, meaning holding both instruction and data. So this level 1 cache is serving CPU. Our hope is that CPU read instruction from level 1 cache. Okay, and our hope again is CPU read data from level 1 cache. Okay, level 1 cache. And level 1 cache is not able to provide data or instruction. You have level 2 cache. Okay, so level 2 cache hopefully can provide instruction and data. But if you cannot find that information, then another layer, main memory, right? So main memory hopefully supply instruction and data to CPU. But if you cannot find it, then last one, secondary storage. It has everything, right? Hard disk or SSD has everything, but super slow. That guy can provide instruction and data. Okay, so that is called memory hierarchy in computer. What kind of memory component do you have in memory hierarchy? And this statement is very intriguing. What does it mean? Taking advantage of principle of locality to present you, right, user, you, with as much as memory as available in the cheapest technology at the speed offered by fastest technology. What does that mean? Very confusing statement, right? That means if you compare the price, price, then price versus capacity. Okay, hard disk or SSD is huge. It is like 1 terabyte or 2 terabyte capacity, right? So think about your computer. You have SSD. So probably 500 gigabyte, right? Gigabyte or 1 terabyte, right? Around that number. And main memory, terabyte. Okay, main memory 8 gigabyte. Gigabyte, right? Terabyte, gigabyte. The order is different, right? And cache, roughly 8 megabyte. Again, the order, right? Unit is different. Mega and giga, right? That is 10 to the power of 9 and mega 6. This one 12, right? 6, 9, 12. Okay. And main memory is pretty expensive compared to SSD. It's small, but you have to pay probably $100. $100, right? For that 8 gigabyte. How about SSD or hard disk? If you want to purchase hard disk these days, then same amount of money, then you can purchase, 1 terabyte or 2 terabyte hard disk. Okay, and cache is even more expensive. So how expensive this chip processor? Intel Core i7 processor. So latest processor, probably you have to pay $300 or more. Intel Core i7, right? Latest processor from Intel. And the thing is, almost of half of this Core i7 is used by cache. Half of real estate. Real estate is used by cache, meaning the cache price divide by 2 roughly, right? Then $150. 8 megabyte, but very expensive, right? Right? Big, small, big, very big, right? Super small, right? But the same price roughly, right? So that means, so what do you want to achieve? What do you want to achieve? Employing this memory hierarchy is that even though you have this slow, very big, but very slow memory, main memory. Okay, but by placing this cache, I want to give you very pleasant illusion. What is the illusion? Okay, even though I have big, I have very big but slow main memory. But the illusion is I feel like I have a very big and also super fast, slow, fast. Okay, same size, but I can give you that illusion. Okay, I have big and also super fast main memory by placing this cache. Okay, that is the purpose of placing the cache. How come? I'm going to explain. Okay, this cache is exploiting principle of locality in your program. Okay, so let's talk first about this locality. What do you mean by locality? In Korean, 지역성. Okay, let's talk about that because we have that terminology. Okay, this one. Okay, 방주영. 백민규.
Why caches work? The size of cache is tiny compared to main memory. How to make sure that the data CPU is going to access is in caches. Caches take advantage of the principle of locality in your program. Temporal locality. If a memory location is referenced, then it will tend to be referenced again soon, so keep most recently accessed data items closer to the processor. Spatial locality. If a memory location is referenced, the locations with nearby addresses will tend to be referenced soon, so move blocks consisting of contiguous words closer to the processor.
Okay, thanks. How come cache is working even though cache is small? Okay, so it is able to, even though cache is small. This guy is able to provide instruction and data to CPU most of the time. Okay, let me repeat that. Even though cache is small, okay, small, right? 8 megabyte, main memory 8 gigabyte. Even though it's very small, cache is able to provide the data or instruction CPU requested almost all the time. How come? How come? So that means you don't have to access CPU. Okay, you don't have to access this main memory. You don't have to access main memory most of the time. Cache will do that service. Okay, instruction and data supply to CPU. Okay, how come? Because there are two kinds of localities in your program. Localities. Okay, first one is temporal locality and spatial locality. I'm talking about your program, not my program. My program, the program I wrote or I write, and program you write, okay, has that locality characteristic. Temporal locality first. In Korean, 시간 지역성. Okay, in Korean, temporal locality, 시간 지역성. Spatial locality, 공간 지역성. Okay, in Korean. Temporal locality. What does that mean? If a CPU access one specific memory location, let's say CPU executed, let's say LW, memory read instruction, right? X5, 4, X3, some memory location, okay? Let's say X0, okay? X0 is 0. So location 4, reading data from location 4, place into X5 register, okay? So location 4, that data. Okay, whatever it is, if CPU execute that instruction and access this data, and the chances are it is very likely to access same information again. Same information again in the very near future. Okay, again, the temporal locality says if you access this information, it's very likely for you to access same information again in the very near future. Spatial locality means if you access this data, and it is very likely to access each neighbor, okay, each neighbor in the near future. Okay, there are very high chances of accessing same information and each neighbor information. Okay, that is called locality. Okay, probably you cannot believe, right? So I have very good program. So look at this very simple program. Assuming that you wrote this program, right? You created array of 3 arrays. Each one has 100 element, right? A, B, C array and local variable D. And you are doing that operation, right? So what is the operation? You are repeating this statement for 100 times, right? So thing is, A0, first element in the array, okay, and first element in array B. Do multiplication, then add D, and store into first element in C array. Okay. Next iteration, I is equal to 1. Then A1, second element. Okay. B1, second element in B. Then add D, right? And then store that into C1, second element in array C. So can you tell me what variable is showing temporal locality, and which one is showing temporal or spatial locality? Temporal locality first. Temporal locality, if you access the same data, if you access one data, and it's very likely for you to access same data again and again, right? So D, think about this D. You are accessing D 100 times, right? D 100 times. And how about, so D is showing temporal locality characteristic. Okay, so if you store data that D in here, okay, if you store D that information here, then next time CPU execute the code, CPU does not have to access main memory, right? Cache is able to provide that information. First time, cache cannot provide that information. But second time, third time, and to the rest, right? And cache can provide that information. And how about that local variable I, 0 to that number limit? Then you increment, right? Same local variable, but accessed very frequently, right? I is 0. Then you are checking I against that constant 100. And then you are incrementing I, right? And that operation, not just one execution, 100 times, right? 100 times. So I is also showing a good temporal locality characteristic, right? So if you cache, so you have local variable I. The first time cache does not have, right, that I, but CPU access I, then CPU will store that information I. So next time CPU, need that information, get I directly from cache, not from main memory. So temporal locality, okay, I and D. How about spatial locality? What variable is showing spatial locality characteristic? What is spatial locality? If you access one location, one data, very likely to access each neighbor data. So array, right? Array. First time A0, B0, C0. So if I draw, so array, right? Array is stored in consecutive memory locations like this. A0, A1, A2, and so on, right? And B0, B1, and so on, like this. So first iteration, you access A0. Next iteration, you access A1. Next, third time, you A2, and so on. So this array is showing very good spatial locality property. Does it make sense? That is locality. Then let's go back. Okay. Okay. So we want to exploit that locality characteristic in your program and my program and everybody's program. Okay. To get very pleasant illusion. Okay. What is that illusion again? Illusion is we have reality. Reality is super big, but slow main memory. Big and slow. But present illusion is big, fast. Big at the same time, super fast. Okay, that is illusion by placing the cache. Okay, so this one, Minji, can you please? Minjun, Sohi, Changho, come on. What are you guys doing?
Who manages data transfer between main memories and disk? By the operating system, virtual memory, by the programmer, files, registers, main memory, by compiler and programmer, cache, main memory, by hardware, cache controller.
Okay, thanks. So it is very confusing. What is confusing? Who manages data transfer between between these two components, right? Between main memory and hard disk, and who manages data transfer between main memory and cache? And cache too. So who manages data transfer between these two? And who manages data transfer between these two? And who right, manages data transfer between these two guys? So the thing is, if you don't have, operating system, we have a very nice the environment, right? We are using notebook and desktop computer where nice GUI Windows, right? Windows OS is already mounted, already ported there, right? But assuming that you don't have that nice operating system, you have some bare metal that motherboard is given to you, right? And you have to write program on top of that. There is no operating system. Then the data transfer between main memory and hard disk, you have to manage the data transfer by software. Okay, explicitly say, okay, I want to place data in some sector in hard disk to some specific place. You have to write that program. But thanks to operating system, you don't have to do that, right? Windows or Linux are doing that data management. But if you dig into the detail of that operating system code, then software code is doing that management, data transfer. The thing is, again, the data transfer is managed by software. Okay, these two. Okay, either by you or operating system. Okay, software manages data transfer between these two. And how about data transfer between main memory and this register? We have CPU, right? Register file. We have X0, X31 register, 32 registers. Who manages data transfer between that guy and main memory? You, right? You wrote some program like this, right? I want to read data from that memory location and place into X5 register, right? You explicitly specify, memory location and register number, right? So you have to do data transfer management, or compiler if you use high level language C. Compiler will compile your C code into instructions, right? So compiler or you if you do assembly programming. How about data transfer between main memory and cache? who is managing data transfer? Hardware. You don't have to worry about that. Software people don't worry about data transfer between main memory and cache. It is automatically, okay? So data in main memory will be placed into the cache automatically by hardware. Someone should design, hardware, right? Cache controller. That is called cache controller. It is cache controller. That cache controller is also pretty complicated, hardware component. So CPU access some information, but cache is not able to provide the data. Then cache controller is initiated. Right? That guy is accessing main memory and place some memory data into the cache. And then cache is providing that information to CPU. So data management is done by hardware. You don't have to worry about that, right? That is good news, right? Any questions so far? Okay, so basic cache operation first. I prepared this slide for those of you who are eager to know the cache operation first. So before we talk about detail, big picture, a little bit detailed, but big picture. So here, that is cache. Okay, we have CPU. Okay, I color coded. Yellow is CPU, and green main memory. We have main memory green. Okay, and cache is located in between. Okay, assume that you want to execute these three instructions. Okay, CPU execute these three. Interpretation, read data from location 4, which is 8 twos, right? And place into X1 register. Second instruction, read from memory location C. See, you have 8 4s. Okay, that should be placed into X2 register. The last one, location 1208. 1208, this one. So 8 sevens, right? And place into X3 register. And this one is cache. Let me explain a little bit detail about the cache structure. This cache has 1024. The first one, second one, and the last one. 1024 entries. So that cache, this one is cache. And you have the first entry number 0. Okay. The last one, entry number 1023. That means you have 1024 entries. Okay. So we have 1024. Each entry is able to hold how big data? 4 words. Okay. So D0, D1, D2, D3. Each one 4 byte. 4 words, right? Four words. That means 4 byte. Each one is 4 byte, 4 byte, 4 byte, 4 byte. So 16 byte. 16 byte, right? 16 byte. So how big? How big is the cache? How big? So 1024 entries, and each one is able to hold 16 byte. That means 1024 multiplied by 16 byte. So 1K, right? 1K. So 16 kilobyte cache. 16 kilobyte cache. Also, this one is called direct mapped cache. Simple cache structure. Most simple cache structure. Direct mapped. We will talk about that. Okay. There are 3 kinds of cache structure. Direct map cache, set, associative cache, and fully associative cache. So we are talking about the most simple cache structure, direct map cache. So 4 words, right? Each one 4 byte. And you have also tag information, tag field, tag. Okay, meaning the why you need tag. It is used to store address information. What address? So what? So main memory is huge, right? Huge. So it's like 8. So 16 kilobyte here. 8 gigabyte, right? Kilobyte, huge, right? So that means cache is so tiny, it is not able to hold everything you have in main memory, right? It is able to only hold small portion, right? Small, okay, I can hold that information. Then you have to record location information, right? What location? This location, this address, right? Which location in main memory, right? And the data is located, that location information. Location, and also data, this data, okay? This data, right? So this data, that data came from that memory location. So cache is holding that information. So that is called tag, right? Tag information, tag and data. Let me do animation. Let me execute. Okay, now we are ready to execute these 3 instructions. First instruction first. Okay, CPU execute that instruction. Then try to search cache first. Okay, this one is called cache line or cache block. Okay, so search the cache. When you search the cache, when cache is searched, only one out of this 1024, only one entry is selected for lookup. Okay, so in this case, in direct map cache case, okay, don't worry about these 2. Okay, so on that example, when cache is searched, only one cache entry is selected for lookup. Okay, then compare that tag information, location information against the memory location CPU requested. So that means, okay, that cache entry is holding the information from that memory location. So first time, right, cache does not have anything. Turn on the computer. Okay, first time does not have anything. So that is called cache miss. So we have cache miss. Okay. Cache miss happens, then what happens is the data will be placed into the cache like this. Okay, like this. So that means what? Let me explain. So let me go back. Okay, CPU requested that information, but cache is not holding the data. So we have a cache miss. Then what happens is cache, this hardware will place not only the data you requested, not only but the data in its neighbor also. Okay, not only the data you requested, okay, these two, but each neighbor, these 4 data into the cache, like this, and record that information. Okay, that the data I'm holding came from that memory location. Okay, so it is tagging. Okay, tagging, right? When you travel, right? When you travel to other countries, right? Then you are, you check in your luggage, right? And you put tag, right? Okay, that package is for me, right? So you are tagging, you're tagging that. You put tags, right? Same tag. The data is from that memory location, right? So this one is called memory block. Okay, so this one, memory block, cache line. A little bit not confusing, but first time a little bit hard to understand. Probably I don't know. Okay. So you have four words, right? That is called cache line or block, cache block. So what should happen is main memory. Right? Main memory is divided into logically divided, not physically. Right? Logically divided into cache line sized. Cache line sized chunk. Okay. So in this case, in this our cache, we have four word, right? So 1, 1, 2, 3, 4. Right? That's 4. Okay, this 4. Okay. So this one is called memory block. Memory block. The first memory block, and then second memory block. Memory block number 0. Memory block number 1. 1, 2, 3, 4. Number 2, and so on. So main memory, right? Main memory is divided, logically divided into this cache line sized chunk. That is called the memory block. Okay. Then when cache miss happens, like that, cache miss happens, then cache will read this whole memory block into the cache. Okay. Not only the data you requested, but the ones in this memory block. Okay, so in other words, data transfer between these two is done by that memory block. You are not just placing the requested one to the cache. You are not doing that. You are 3, 4. So 1, 2, 3, 4. Right? You are placing this whole memory block, okay, to that the cache entry. Okay. Why is that? Why? Because we want to exploit locality characteristics in your program. Again, what locality? 2 localities: temporal locality and spatial locality. What is temporal? Temporal is you requested this data. Okay, I cached it, so I can provide the data to CPU directly. So next time, spatial locality. Next time you request, this one, each neighbor. Okay, I already that data in the cache. So cache, I can provide that information. So cache, we want to exploit that spatial locality, temporal locality properties. Okay, by using this long cache line. Okay. So let me do animation. So now first instruction is done. CPU, let me go back. So first data, cache miss, data is coming in to the cache. Then cache is providing data to CPU. So X1 is now holding this data to A2s. Okay. So then the data in each neighbor within that memory block will be stored into the cache like this. And then location information, this memory block location, okay, will be stored like this. So first instruction is done. How about second instruction? Read from location C. Okay, that's C. Okay, so CPU search the cache first. Okay, and look up and select one cache entry. Then it turns out that cache is holding the information CPU requested. Right? C, the data 8-4s that is in the cache. So cache can provide data to CPU. Cache hit. We have cache hit. Cache hit now. Cache can provide data to CPU. Okay, so now second instruction is done. So last instruction. Read from location 1208. Okay, then look up, select one specific cache entry. So it happens. So I'll explain why it select that cache entry. I'll talk about that, okay, later on. So assume that this cache entry is selected, okay, then it is not holding anything. So we have cache miss. Okay, so then what should happen? The memory block containing this data, okay, this data 23, 23, 23, then memory block. Oh, okay, sorry. 1218, sorry, 1208. 7 sevens, 8 sevens. So memory block containing the data, memory block will be copied to the cache. Then that information is provided to CPU. Then the remaining data will be stored in the cache. And location information, right, should be stored. That is cache operation. A little bit big picture, right? A little bit. I have to explain a little in detail, but big picture. Does it make sense? Any question? So by having this long cache line, you can exploit locality properties in your program. That is important message, right? Cache is trying to take advantage of locality properties in your program, in my program, right? Locality. Temporal locality, you access one memory location, very likely to access same location again and again in the near future, right? And spatial locality, if you access one memory location, very likely to access its neighbor data in the near future. So that is why cache line is long, and you have cache miss, then memory block containing that data. The memory block containing the data will be placed into cache. Whole memory block, not just specific data you requested. Okay. Because we place this whole memory block, okay, we can take advantage. We can take advantage of locality properties. Okay, why cache works? Temporal locality, spatial locality. Okay, this one I did this, right? So think about this. This is also cache structure. Cache without tag information, only data part. Okay, here. Okay, only data portion. So again, at the beginning, when you turn on the computer, cache is not holding anything. It is, nothing. It has nothing. So think about that. You are accessing A0, B0, D, first iteration, and C0, right? A0, B0, D, and C0. So first time access A0, you have cache miss, right? Because cache has nothing, right? So then cache will place whole memory block. This whole memory block, right? In this case, you have 1, 2, 3, 4, 5, 6, 7, 8. 8 words, right? So in that case, memory block size, right? 8 words, right? 8 words and 8 words, right? So the memory block containing requested data will be placed. Right? Say A0, A1, A7. Even though you requested only this A0, cache will place this whole memory block A0 to A7 into the cache, right? Like this. A0 whole block A0 to A7. How about B0? Same thing, right? Cache is not holding the data, so we have cache miss. So here, memory block. In this case, in this example, memory block containing B0 has that data, B0 to B7 and A99, A96. That is a memory block in main memory, right? And how about D? Okay, when you access D, or cache miss, right? So cache will place whole memory block, and that memory block should contain D, right? And in this case, it happens, that memory block happens to have this data as well, C99 to C96, right? So that information is stored in the cache. So second iteration, I is 1. Then you are accessing A1, B1, D, C1, right? So look at this. A1 is already in the cache. So you have cache hit. B1 is also in the cache. So you have cache hit. How about D? D is in the cache hit. C1 is in the cache hit. So cache is able to provide that information. So locality, okay, localities. Okay, now our details. Okay, some terminology. Seungmin, can you please?
Cache terminology, block or cache line, the minimum unit of data present in a cache. For example, 64-byte block in Core 2 Duo. Hit, if the requested data is in cache, it is called a hit. Hit rate, the fraction of memory accesses found in caches. For example, CPU requested data from memory and cache was able to supply data 90% of the requests. Then the hit rate of the cache is 90%. Hit time, the time required to access the data found in cache. Miss, if the requested data is not in cache, it is called a miss. Miss rate, the fraction of memory accesses not found in cache. 1 minus hit rate. Miss penalty, the time required to fetch a block into a level of the memory hierarchy from the lower level.
Okay, thanks. Some terminologies first. I already explained to you about block, memory block, or cache line, right? The cache line size. Okay, in this case, 16 byte. 16 byte. If the cache line size is 16 byte, then main memory will be logically divided into 16 byte chunk, 16 byte chunk, 16 byte, 16 byte, 16 byte, and so on. Okay, and a real machine example, Intel CPU, not only Core Duo, but the CPU you are using, Core i7. Okay, Core i7 has 64 byte cache line size. Okay, that means here you have D0 D divided by 4, then 16, right? D0 to 16. Then main memory will be logically divided into 64 byte. 64 byte chunk, 64 byte first, second 64 byte, third 64 byte, and so on. Okay, so real machine example. So cache line size, that is typical number, 64 byte. Okay, that is typical number. So data transfer between cache and main memory. Okay, data transfer between cache and main memory is based on that memory block size, 64 byte data copy, okay, to cache. Hit, I already, right? We know hit and miss, right? Very intuitive terminology. So if the data is found in the cache, okay, data, the CPU requested some information, and that is found in the cache. We have hit, right? So how many times cache is able to supply information to the CPU? Hit rate. So 90% hit rate means 90% hit rate, meaning 9 of, right, 10 requests from CPU are serviced by cache, right? So assuming that you have 10 LW instructions executed by CPU, 10, and 9 instructions are serviced by the cache. Then we have a 90% hit rate. 90% hit rate, that is equal to 10% miss rate. Simple, right? 10% miss rate. 10% miss. So hit rate, miss rate. Hit rate, miss rate. Hit time is what? Cache can provide information, data or instruction to the CPU. Then how long? How long does it take? It is 1 cycle, 1 clock cycle, or 2 clock cycle, 3 clock cycle. That latency, the time. How many clock cycles? Right? How many clock cycles? Right? 3 clock cycles means you have to wait. CPU should wait 3 clock cycles to get information. Miss penalty, last one. Miss penalty means additional clock cycles. Right? Cache is not holding the information CPU requested, right? Then the information should be copied from main memory to cache first. Then cache can provide data information to CPU. Miss penalty means that is hit time, right? Hit time. Okay, hit time. Miss penalty is this one. Miss penalty. Additional clock cycles. CPU should wait. Okay. In case of miss. Time required to patch a block into the level of memory hierarchy from lower level. This is the lower level. Okay, this is higher level. Okay. Some terminology. Okay. Okay, direct map cache. I already explained to you. Not detail, but a little bit. But let's talk about the most simple cache structure, which is direct map cache. This one, Jisang, can you please?
The simplest cache structure, direct mapped cache. Each memory block is mapped to exactly one block in cache. Lots of memory blocks must share a block in cache. Address mapping to cache. Have a tag associated with each cache block that contains the address information. The tag is the upper portion of the address required to identify the block.
Okay, thanks. This one we have tag. Let me draw same configuration. We have cache. So particularly, this one. Rotate, rotate, right? Rotate counterclockwise, right? That. So we have data. Okay. So cache entry number 0 to number 7. Number 7. Then it does not specify the cache line size. Okay, line size. So conceptual explanation, right? So let me do this. Let me say better to explain with an example, right? Let's say 16 byte. Okay, 16 byte cache line size. Cache line. Then main memory. Main memory. So 4 words. 4 byte. 4 byte. 4 words, right? D0 to D3. So main memory again logically divided into that. Let's say each one is 4 byte. So first memory block and second memory block, and then third memory block, right? Cache line size number 0, number 1, number 2, and so on. Logically divided into this chunk, right? So I'm trying to explain the mapping mechanism right here, mapping mechanism. Here, so here, each one, okay, so crowded. So I cannot draw many memory blocks. First, second, third, and so on. I want to draw many different memory blocks. So let me change the picture. Let's say times. So let me divide memory into cache line sized. This one is cache line sized block. 16 byte, right? 16 byte, 16 byte, 16 byte, 16 byte. Then in direct map cache case, the mapping mechanism is very simple. Mapping mechanism. So location 0. Okay. First memory block goes to first cache entry. Second memory block goes to second. Third goes to here like this. Very simple. I should have drawn 4 only. Too many. Okay. Then this one memory block number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then that memory block is mapped to wrap around, right? Then like this, simple. Like this, like this. Okay. So thing is first 8 memory block. First, because we have 8, 1, 2, 3, 4, 5, 6, 7, 8, 8 cache lines. So first 8 memory blocks are mapped to cache, and next second 8 memory blocks are mapped to cache, and then and so on, right? You have 8 memory blocks mapped to here, and so on. Right? So that is the thing, right? Mapping mechanism. Okay, here first memory block in this green chunk. Okay, green chunk. So same cache size, right? Cache size and this cache size. First memory block in this green chunk map to first cache entry. Second, right? Second memory block in green chunk map to second cache entry. Okay, same thing goes to here, yellow chunk, right? First memory block in yellow chunk, okay, map to first cache entry. That means the message is, many different memory blocks in this figure. Second memory block, right? Second memory block in green, second memory block in yellow, second memory block in orange, purple are mapped to same cache entry, same cache entry. And also fifth one in green, fifth one in yellow, orange, purple are mapped to same fifth cache entry. Okay, the message is you have to store not only data but also location information. Okay, so we will talk in detail about that. So we ran out of time. Okay, any question before letting you go? Yes, yes. Shion, yes, yes. But we will talk in detail. Okay, we will talk in detail. When you execute LW instructions, okay, LW instructions. When you execute, for example, okay, now we have slide. I don't have to draw. The question is, I showed the animation, right? This one. So when CPU execute that instruction from location 4C1208, why do you have to select that particular cache entry for this last one? And first two, why do you have to select? Why first two, right? First two instructions. Why do you have to select first one? Yes, because of that mapping mechanism. So I'll talk in detail. Okay, I'll explain in detail next time. Okay, any other questions? All right, I guess that's it for today. See you on Monday. See you on Wednesday. Bye.